All right, developers, welcome to this explainer. Look, if you've spent your entire career writing explicit code, you are very used to a world of absolute rules. You write a function, you pass in some data, and you get a guaranteed fully deterministic output. It's comfortable, right? But integrating AI into your applications requires a total paradigm shift. Today, we're moving from traditional coding into the art and science of prompt engineering. We're going to break down how to actually guide large language models to do exactly what we want, leaning heavily into the principles outlined in Chapter 4 of The Developer's Guide to AI. Mastering this stuff isn't just some neat party trick. It is literally the fundamental difference between building a brittle, unpredictable AI feature and a robust, highly scalable application.
Here's our roadmap for today. We're going to cover programming versus prompting, when to actually use LLMs, the 5 core elements of a prompt, tokens and context windows, how to avoid runaway costs, and finally, choosing a model. Let's just dive right in.
Okay, Section 1. Programming versus prompting, the big paradigm shift.
The absolute first thing we need to wrap our heads around is that LLMs are not magic, and they certainly don't think like you or I do. Traditional programming relies entirely on explicit logic and exact matches. You tell the compiler or the interpreter exactly what to do, step by step, and it executes those commands flawlessly. Prompt engineering, on the other hand, is all about steering a probabilistic model. Under the hood, an LLM is really just predicting the next most likely token based on billions of mathematical weights. And honestly, that's where most developers get caught off guard. You might feed a model a simple prompt and get a decent answer. But if you tweak just 2 or 3 words in your instruction, you completely alter the probability distribution of the model's response. Suddenly, the system behaves in an entirely different way, even though there was zero change to the underlying code. Grasping this probabilistic mechanism is what actually gives you control over the format, the structure, and the reliability of your AI features.
Moving on to Section 2, when to use LLMs. Finding the right tool for the job.
Because LLMs are probabilistic, we absolutely should not be using them for everything. Seriously, think about parsing an email address from a string of text. That is a highly deterministic task. You can accomplish that efficiently through traditional code and a standard regular expression. Using a massive LLM to do regex is just a huge waste of compute. But on the flip side, consider classifying text sentiment. Trying to write brute force rules to determine if a tweet is positive or negative, that's nearly impossible. Edge cases, like sarcasm, will instantly break your regular expressions and keyword matchers. And this is exactly where LLMs excel. They utilize deep neural networks to understand semantic intent and complex linguistic patterns rather than just matching characters. If you have a task that involves natural language ambiguity, something that feels impossible to solve with traditional if-else logic, well, that is your clear use case for a large language model.
So, once you've identified the right use case, you have to actually write the prompt. And as developers, you have a distinct edge here because you already know how to turn fuzzy ideas into concrete step-by-step instructions. Good instructions generally rely on 3 pillars. First, they've got to be detailed. Instead of vaguely asking a model to summarize this text, a detailed prompt asks it to summarize this text in exactly 3 bullet points, focusing exclusively on action items. Huge difference, right? Second, prompts must be clear. Use direct active verbs and avoid industry jargon unless you've explicitly defined it for the model beforehand. And third, they must be concise. You really need to strip away any conversational fluff. Unnecessary words don't just waste space, they actively distract the model's attention mechanism away from your core instruction.
Which brings us to Section 3, the 5 elements of a prompt, or how we actually structure these requests.
A production-grade prompt is never just a single sentence you fire off into the void hoping for the best. It is a highly structured request. Let's walk through this by imagining you're building an automated support bot. Your prompt starts with an instruction. This establishes the persona and the core task, like telling the model it's a helpful assistant designed to summarize support tickets. Second is the context. This would be the user's historical account data and previous troubleshooting steps. Third, you provide examples, literally, actual sample input-output pairs showing the model exactly what a good summary looks like. Fourth is the query itself, the brand new support ticket text you need processed right now. And finally, the output format. Here, you demand a specific response structure, explicitly asking the model to return the summary as a valid JSON object so that your application's downstream code can actually parse and use the answer without crashing. Now, in industrial-strength AI applications, that context element is absolutely everything. We do not want the model guessing or hallucinating answers based on its generic training data. We want it grounded in our specific, factual reality.
This is where architectures like RAG, or Retrieval Augmented Generation, come into play. When a user asks a question, a RAG system uses a vector database to search through your company's internal documents for semantic matches. It retrieves the most relevant paragraphs and dynamically injects that raw text directly into the prompt string as context, right before sending it off to the LLM API. It essentially gives the model an open book test, which dramatically increases its accuracy.
But that begs a pretty obvious question, right? If providing context makes the model infinitely smarter, shouldn't we just dump our entire customer database into the prompt every single time? I mean, how much context is too much?
That takes us to Section 4, Tokens and Context Windows. Basically, our new compiler limits. To really understand our limits here, we have to look at tokenization. When you send a prompt over an API, the language model doesn't read text the way you and I do. It breaks your text down into tokens. Very common words might map to a single token, but complex words or snippets of code are split into multiple chunks, or syllables. As a general engineering heuristic, about 750 English words equal roughly 1,000 tokens. And here is exactly why the math matters to you. Every single token you send, and every token the model generates in response, costs compute time and real money. The larger your prompt, the higher your application's latency, and the larger your cloud bill at the end of the month.
Because processing all those tokens requires immense computational power, every model has a context window. Think of this as the absolute maximum memory buffer for a single interaction. You literally cannot stuff unlimited data into an LLM. If you exceed the context window limit, the API will either throw a hard error, or worse, it'll silently truncate your text, completely destroying the integrity of your instructions. This introduces a major architectural challenge for developers. Say you're building a chatbot. Eventually, you hit a wall where the chat history exceeds the context window. So you have to engineer solutions like dynamically summarizing older messages just to keep the conversation state small enough to fit inside the model's strict limits. But listen, even if you manage to stay technically within the context window limit, packing a prompt too full leads to a mechanical failure known as the lost in the middle effect. Why does this happen? Underneath the hood, an LLM's attention mechanisms naturally apply heavier mathematical weights to the beginning of a sequence, where your instructions usually are, and the very end of a sequence, mostly due to recency bias. If you stuff 50 pages of bloated background data into the middle of a prompt, the model's attention just gets blurred. It will frequently ignore critical facts buried in that middle section, severely degrading the accuracy of its output. Small, precise, highly relevant context will always outperform massive data dumps. Okay, Section 5, Avoiding Runaway Costs, or How to Protect Your Company's Runway. To highlight the massive financial stakes of ignoring token limits, Chapter 4 shares this brilliant and honestly terrifying cautionary tale. A startup team rolled out a new bulk document processing feature powered by AI. When they got their first usage charges, they were sent into absolute sticker shock. Their API bill, which normally hovered around $1,000 a month, instantly skyrocketed to nearly $10,000. The root cause? A total lack of prompt engineering. Instead of retrieving specific context, they were sending massive, unoptimized payloads, effectively dumping entire, unfiltered database tables into every single user request. They were sending tens of thousands of tokens when a few hundred would have easily sufficed. Doing the math on 100,000 daily requests, that bloat compounds instantly. Efficient prompt engineering isn't just about getting better answers. It is literally about physically protecting your company's financial runway.
Finally, Section 6, choosing a model and selecting the right LLM for your needs.
Once your prompts are properly optimized, you have to select the right engine to run them on. Think of this as your architectural trade-off matrix. First up is the performance to cost balance. You simply do not need a massive trillion-parameter model to perform a simple JSON formatting task. Models like GPT-4 or Claude 3 Opus are incredibly powerful, yes, but they are expensive and they are slow. For highly scoped tasks, smaller models like GPT-4 Omini or Claude Haiku are entirely sufficient, and they come in at a fraction of the latency and cost. Second is licensing. If you choose to run open-weight models locally, you must ensure the underlying license actually permits your specific commercial application. And third is data privacy. If you're hitting a proprietary hosted API, you have to read the fine print to ensure they aren't using your company's proprietary data to train their future models. Compare that against utilizing a self-hosted open-weight model where you retain absolute privacy.
For example, when evaluating those licensing constraints out in the wild, look at Llama 3.2. It's an incredibly capable open-weight model that allows commercial use, but it ships with highly specific restrictions. If your application scales to more than 700 million monthly active users, the standard license is totally void, and you have to negotiate a custom agreement with Meta. Furthermore, strict regional data regulations have actually led to a total ban on the use of Llama's multimodal versions within the European Union. These are the gritty, production-level details you have to navigate every day. Choosing your AI engine is never just about which model performs best on a leaderboard benchmark. It requires a careful balancing act of cost efficiency, legal compliance, and ironclad data security.
We've covered a massive shift today, moving away from rigid deterministic coding to the nuanced art of probabilistic prompting. We've explored the core structural elements of a perfect instruction, the rigid memory constraints of context windows, the mechanical reality of token costs, and how to architecturally choose the right model for the job. So I want to leave you with this provocative question as you head back to your desk. Look at the application you're building right now. How could your most complex, fragile, brute force logic be completely replaced today by a well-crafted probabilistic prompt? Think about your backlog. Thanks for joining me on this explainer, and happy prompting.